What if we combine all the Kuiper Belt objects into a single planet? How massive would it be? And what would happen to it? In this video, I'll run this experiment in Universe Sandbox and show you the result. Let's go. The Kuiper Belt is at the edge of the solar system, right here beyond Neptune's orbit. And also, beyond the Kuiper Belt, there's a region called the scattered disk. A number of different dwarf planets and objects also orbit in this region of space. In our experiment, all these objects from these regions will be merged together into one single planet. To merge these objects, I'll use the same method I used in a recent video where I combined asteroid belt objects. I'm just going to go ahead and delete all of these objects right here. I'll also remove all the objects orbiting near Neptune and Saturn. And I'm also going to delete the planet Neptune. Now we're left with only the Kuiper Belt and scattered disk objects. Now I need to select them all, go into settings, and then into motion. And here, I'll set their distance to 3,000 kilometers from each other. I'll also reset the velocity for all the objects to 0. And look at that. All these objects are now, roughly speaking, in one place. But that's not all. Some dwarf planets have their very own natural orbiting satellites, of course, and we won't forget them. We are also adding moons to Pluto, adding Eris's moon, adding Haumea's moons, and adding Quaoar's moon, the moon named Waywat. Interestingly, Orcus and Makemake also have their own moons, but unfortunately they aren't in the simulator. Now I see that all these moons are quite far away from the main Kuiper Belt objects, so I need to select them like this as well. And I'll move them closer to the other objects too. Haumea and Quaoar also have rings, so I won't forget about those. Adding Haumea's rings and adding Quaoar's rings. It has two layers, an inner and an outer one, and this is what it all looks like. In the simulation settings, everything will be turned on. Gravity, collisions, fragment formation, and temperature. This will be the first simulation. And now I'm starting the simulation. Oh, incredible, right guys? Everything is so bright. And as we can see, Pluto is the winner in this simulation. An incredible cloud of dust. I'll speed up time. There's Charon flying in for a collision. And we see that many fragments were ejected. High temperatures and lots of debris flying away. A little bit of time has passed. We see Pluto looking like this. It's very flattened, likely because it's spinning so fast on its axis. And we see Charon orbiting right here. I'll slow down its speed, so it definitely crashes into Pluto. But Charon seems to be the smartest moon, having settled into orbit around Pluto. Now everything has definitely collided with this Pluto. Look at the massive temperatures on it. I'll speed up time, let it cool down, and see what we got. Pluto has cooled down now. This is how it looks, egg-shaped like Haumea in the solar system, but even more flattened. A day on it is just over 2 hours long. And in the end, we see that in this simulation, its mass is almost 1 lunar mass and the radius is 1,625 kilometers. But this, guys, is not a complete simulation, because many fragments burned up and many fragments simply flew away. And now I'll collide all these objects, having first disabled temperature and fragment formation during collisions in the simulation settings. This way, it'll be possible to merge them all into one body, without any losses. I also opened Pluto's characteristics. Look at the mass and radius indicators. They will be increasing here. Well, I'm betting on Pluto that in this simulation it will win again. And so, I'm starting the simulation. 5 minutes per second are passing for us. We see that Pluto's mass and radius are already growing. Yes, and we see that Pluto really won. Not everything has collided with Pluto yet. Here we see Charon flying, and here we see a number of other objects that are just flying away from Pluto. I don't want them to fly away. I'll select them all like this, and we'll reset everyone's speed here. Let's see what final size Pluto will get. And only Charon is left. Charon will now graze it tangentially at one of the poles. Oh no, it hasn't been absorbed yet. Oh my goodness, Charon, what is this? I'll reset Charon's speed once more. Well then, Charon is returning. And now, the final correction of Pluto's mass and radius. Everything collided with Pluto, nothing else is left. And Pluto was spun too much around its axis again, so it took on this shape. In the end, we have an object with a mass of 1.29 of the moon's mass and a radius of 1,842 kilometers. And the rotation speed around its axis here is 2.5 hours. Let me set it here to, say, 30 hours for a day. Let it become a perfectly round shape. This will be much better. So guys, we've formed an object with a diameter of 3,684 kilometers. I'll save this object, and now I'll place it in the solar system in the Kuiper Belt. Here I have my saved Pluto, and I'll put it not far beyond Neptune's orbit somewhere here. Here you go, this Pluto with a radius of 1,842 kilometers. I'll also say that such a planet has an axial tilt of over 45 degrees. I was also surprised that the atmospheric composition says 111 Earth atmospheres of water vapor, but it's as if visually you can't see any dense atmosphere here. Maybe the simulator bugged out, who knows? And now let's compare this Pluto with the old Pluto. On the right we have the old Pluto, on the left the newly formed one. This is the difference between them. In Universe Sandbox, the radius of the original Pluto, this one, is 1094 kilometers. But when I looked on the internet, the radius there is almost 100 kilometers larger. So I don't know who to believe and who not to. But for the calculation, I'll take the data from the simulator. And having calculated the difference, this new Pluto is only 748 kilometers larger. Of course, I expected a much bigger result because there are many dwarf planets here. Eris, Makemake, Sedna, and so on. They should have made the planet larger, but as you can see in the simulator it turned out like this. And now let's add a few more objects for comparison. Let's take our satellite, the Moon. We can also compare it with Mercury, the smallest planet in the solar system. And let's also compare it with Ganymede, the largest moon in the solar system. Let's use the chart mode tool. By the way, it's very strange why the simulator thinks Ganymede is smaller than Mercury. On the contrary, Mercury is smaller than Ganymede. Well, anyway, okay. In the center, you see our newly formed object. And as we can see, it's larger than the Moon. And of course, larger than the original Pluto. But if you look closely, it's not much smaller than Mercury in size. But with Ganymede, the difference is already greater. And now, just like in that video with the asteroid belt merger, I'll merge all these compared objects, starting the simulation. 1 minute passes per second. I'll put them on such a close orbit so they slowly crash into each other. Well, of course Mercury should win here. Water has already started pouring onto it, as you can see. And clouds have appeared on Mercury. Quite epic. And here you see what happened. Which object do you think is left here? It's Ganymede. How unexpected, but Mercury definitely collided here. Time has passed. Ganymede cooled down to over 20 degrees Celsius. We see such a cloud around Ganymede, and basically what Ganymede has turned into. We see a lot of liquid water on it. Most likely that's the case. And we see that it's very flattened. A day on it is an hour and a half. That's very fast. Let's make it 24 hours. Well, it already looks much nicer and better this way. Otherwise, all the water gathered at the equator due to the fast rotation. In general, the little planet looks much nicer now. Strange. This object even became smaller, 1,311 kilometers in radius, and the mass is 1.34 of the Moon's mass. Due to the distance from the Sun, it looks quite dim. Time will pass, and the planet will become completely icy. This Ganymede has formed such an orbit around the Sun. We see that it's elliptical, very elongated. Let's conduct another experiment. First of all, I'll level its orbit. And now I'll move this planet to the habitable zone and see what it becomes there. I'll set the orbital period to about 1.2 years, and thus our Ganymede ends up a bit further out than Earth's orbit. The temperature here is falling quite rapidly, and it's already below zero everywhere. We see there's land only at the poles here. Otherwise, the territory is flooded everywhere, and the temperature is already minus 33 degrees Celsius. I think it's clear that it will be very cold here. Regarding the atmosphere, it's very thin here, mostly consisting of water vapor, and the pressure here is very tiny. What if we move the planet closer to the star? Now our object is between the orbits of Earth and Venus. A little time has passed and we see the temperature is really rising, and maybe it will be just right here. Well, the simulator shows that everything is already settled. Minus 3 degrees Celsius average, but 16 degrees Celsius at the equator. The likelihood of life is very slim. In the simulator, clouds are disabled by default here for some reason. I've noticed this with moons multiple times. Anyway, I've enabled them. So in the end, we've got this water planet where there's stable liquid water at the equator and it's colder with ice near the poles. But there is no life on this planet. If you like this experiment, please give it a like and leave a comment. Thank you very much.